Welcome back. I'm Lisa Blackburn, and this is my YouTube channel for everything I want to talk about in science and math. And today we are talking about AP Chemistry, Unit 4, Chapter 9, Molecular Geometry and Bonding. So this is a fun one. Well, I think so. I always like this one. All right, so what we're going to do is before we do anything, we're going to talk about we're going to sort of illustrate the concepts in this with marshmallows and pretzels, okay? So everybody take your marshmallow, and your pretzels represent electron clouds. So are they positive or negative? Negative. Are they going to attract or repel? Repel. So this is going to just represent an atom with its electron clouds coming out of it in a chemical bond. And if it has two, how would you insert them into your atom here as far away from each other as possible? Everybody do that with your pretzels. Okay. That's Leslie. No, hello. Tyler, you have a visitor who needs to talk to you for 2 seconds. Where's my bride? Where's my snack? What do you got? All right. Okay, so did everybody get them as far apart from each other like this? Okay, so how many degrees in geometry class is that? 180. And if this was a molecule, what shape would we call this? A line. So we would call it linear. Okay, now take a third electron cloud and poke it in as far away from each other as possible. Is this correct?
No.
No, why not?
Because they're not as far away as they could be.
And so how many degrees apart do I have these two?
180.
And how many degrees apart do I have that? 90. So this could be further, right? Okay, so how should I do it?
120 degrees between.
They need to be 120. Okay, and do you remember what this is called?
A triangle.
It's like a triangle. It's called trigonal planar. Because see how it's in one plane, remember geometry class? And it's a triangle. And what's the bond degrees? Lily said it. What is it? 120. Okay, so now everybody try 4. Language.
If I was a teacher, I'd go beat him up right now.
I like my job. So I used to teach, at Pebblebrook, and there was this sweet old lady teacher, and she used to be a nun before she became a teacher, but she fell in love and gave up her nun to get married, and so she had been teaching a long time, and she said one day, you know what's wrong with our school system? Is we can't beat them anymore. They took out paddling. And she was just this tiny little sweet lady, and she wanted to beat the children. I'm like...
I agree.
That would have been paddling was gone before I was in elementary school. That was a long time ago, so I can't even imagine. Never had paddling. Okay, am I right? Is this good?
Yes.
No. What's wrong with mine?
Yours is now like 120.
No. What's that angle?
It's supposed to be
90.
90.
It's 90. I can do better than 90. How do you do better than 90? You add a new plane, right? This is 2D, and we need it to be 3D.
I am so smart.
We got to get out of our 2D thinking and get to 3D. Okay, so someone said it earlier. It starts with a T. What is it? Tetrahedral. Does anybody remember the bond angle?
It's like 97.3 or something.
No.
No, that's worse than 90. Wait, I know it's better.
Remember when I said you were so smart?
It's 107.5.
You're close, Evan. You really were.
Right? No, 109.5. I'm doing I just mixed in my head. If it has an unshared pair. It's 109. 109.5. Okay. So now you can eat your lab equipment if you want to. You don't have to.
So for that one, was it like the same as the 120 and then there was just another one sticking out of the other one?
What? If it's like 120 what?
So like when you made the fourth one,
Uh-huh.
where did you put them?
Oh, so what you do is you make it like a three-legged stool with one coming out the top. And that's a tetrahedron. And if you do it exactly right, any way you turn it, it's still shaped the same way. All right, so with that little review in mind, I think this isn't all that hard. Okay, so one of the ways you can tell one of the ways that we look at structure is by Lewis structures, and we talked about that last time. And they give you the atomic connections. I need to make this a little bit bigger. They tell you the atomic connections, which atoms are physically connected, but they don't tell you anything about bond angles. You can do the Lewis structure and find out what's connected, okay? But by noting the number of bonding and non-bonding electron pairs, that's what was like our pretzels, we can easily predict the shape of the molecule. Oh, that's so little. It says shape. All right, so these are the ones we just did, some of these, and we're going to talk about them all. So this is our first one we did, and it is a linear. Our second one, this one is called bent. I like these names. They're not like crazy. They go with what they look like, right? That looks bent, yes?
What is that below number say again?
That one says shape. Shape. I know my blank wasn't big enough.
I'll learn that too.
I had these already and didn't want to retype them. So I just went with the blanks being little and was like, oh, I'll write little, it'll be fine. Okay, so this one is what we did with 3, trigonal planar. Okay, this one is trigonal pyramidal. I'm going to write it up here so I can write bigger. So this one is like the tetrahedron, but it's missing the top little part, the one that goes straight up, trigonal pyramidal. And this one is called P-shaped. See? Aren't these good names?
Incredible.
I like them.
Okay. In order to predict molecular shape, we assume the valence electrons repel. They repel each other. So there's our little repulsive child sticking his tongue out at everybody. Okay. All right, so now that's some of the names. We're going to learn more, but that's some of them. And now we're going to talk about the bond angles.
That is not Tyler.
Okay. So here, in this thing, the A is the central atom and B is the surrounding atoms. So here we have one central atom and 2 surrounding ones. And our angle, y'all already said, is 180 degrees. So that's our linear. Here's our trigonal planar. And what did y'all say the degrees are?
90.
No?
120.
120. Okay. So that's one central atom with 3 around it. This is a central atom with 4 around it. And that's our 109.5, our tetrahedron. Okay, this one, notice, let me get my dog toy. Oh, look, see, I ran another road race. I didn't win. But it was fun. It was at the aquarium.
When was that?
It was Saturday. And then we went and saw the fish. I did better. I moved up. I was like 26th in my age division. I just don't like that course. You start off running like the first half mile just uphill. It's not fun. Okay, so this is my dog toy. And so this is how some of them go. So notice the orange one goes up and down. And then on this one, 3 come out around. Mine has 4. So just imagine that instead it's 3 like that. Do you see it? So that is the shape. One going up, one going down, and one in a little triangle going around it. Okay? So this one has 2 different angles. From the top to this radius going around, what angle is that?
90 degrees.
90 degrees. Could you see that? So this one right here up top is 90, and this one going around, there's 3 of them, so what is it?
120.
120. See, this is not hard.
Yeah, if I know it, guys, you should know it.
Not hard. All right, and so this is just like my dog toy. 1 going up, 1 going down, and 4 going around the middle.
So you just know.
Okay? So this is going to be 90 all around. They're all 90s. And that would be with 6 things going around. Now, we already talked about the names of these, linear, trigonal, planar, and tetrahedron, but we haven't talked about this one yet. This one is called trigonal bipyramidal. Doesn't that sound smart? Trigonal bipyramidal.
Did we learn about all of these in honors? Or just...
No, we didn't learn about these last 2 in honors. See, this class is honors plus a little bit more. That's what we do every chapter, honors plus a little bit more. Okay, and this one is called an octahedral. It's like a tetrahedral, but it's an octahedral. So see, we got to learn 2 new things already, yeah? Okay, so once you know these shapes, you can usually figure out any other shape. Just like how I showed you that the trigonal pyramidal was just a tetrahedron with its top taken off. That you, for any shape, A, B with some number, molecule, you can usually derive the shape from one of these. For example, you start with the tetrahedral, and then you can, if you take off the top, you get the trigonal pyramid. Okay, and then if you take off another one, you get bent. So this is like methane, but then on ammonia, it's like this, but on top, instead of having a bond, it's got an unshared pair, but it's called trigonal pyramid. And this is like water, oxygen and 2 hydrogens. It's just like the tetrahedron, but oxygen has 2 unshared pairs. And so what's left, if you take off the unshared pairs, is bent. How do we feel about this?
So when it says like the ABN molecule, is like the number just for how many sides it is?
How many things that are stuck to the central molecule? A is the central atom, and B is things stuck to it, and N is how many things are stuck to it. Okay, so Vesper. So this is a thing that was in our standards for honors, and it said not to teach the students Vesper. But I always kind of threw it in a little bit because it just makes more sense. And I think so does Miss Korn. We've talked about it before. So what determines the shape of a molecule? Electron pairs, whether bonding or non-bonding, repel each other. I'm going to write it down here because I didn't give myself a big blank. It all has to do with the repelling. Just like our pretzels repelling each other and our marshmallow, it gives it the shape. Because remember, they're likes and likes repel. Each non-bonding pair, single or multiple bonds, produces what is called an electron domain. Or just the domain for short, sometimes you hear it. An electron domain about the central atom. So like this oxygen has 3 unshared pairs and a bond. So if we could see that, they would be arranged around that oxygen like a tetrahedron. This oxygen has a bond, another double bond, and a unshared pair, a double bond is considered one thing. It's one negative clump. So this would have three repelling each other around, and they would naturally form into that 120 trigonal planar shape. And then over here, this one's got three also, two unshared pairs and then the double bond. Okay, so this is how Vesper predicts, and we already looked at it, that here we've got 180, 120, 109.5, 90 and 120, 90, 90, and we looked at that the other one. Not hard, is it? So you do have to memorize for the AP test these numbers and the names. Okay, so we can use electron domain geometry to help us predict the molecular geometry. So this is called what kind of structure? Lewis. So that's our Lewis. And it does not tell us anything about the shape. The next thing we can look at is electron domain geometry. And that would be like that one. You know, it's got the little pyramid, it's got dashed lines. This triangle means it's coming out towards you like that. And then this last one is called molecular geometry. So that's what those different things are. Okay, so now we're going to talk about how we can know what shape they are. And it has to do with how many electron clouds it has. That's our friendly little electron cloud encouraging us to do this well. Okay, so first of all, if it has, so it's always going to have at least two. If it has two electron domains, oh, I'm on the wrong one. I'm like, that's not right, because you're on the wrong page. Okay, go back up here. Okay, this one has two electron domains, two things coming out of it. So it has two clouds coming out of it. It doesn't have any unshared pairs here. It's just got two domains. The shape is linear, and an example of this is carbon dioxide. It's got a carbon in the middle, a oxygen on each side. It's a linear molecule. Okay. Next, that's really about all you can do with two. The next is three electron clouds. And if we have all three of them making bonds and none of them not making bonds, it looks like that, trigonal planar. An example of this is BF3, bromine trifluoride. Yep. Okay, but it also, you could have three of them again, but two of them as bonds and one's an unshared pair, and it looks like this, and then it's called bent because it's got this one. I always think it looks like a little alien head. It's got one little unshared pair there. An example of this is nitrogen dioxide. Okay, this is all pretty easy, right? Moving right along.
Miss Blackburn,
Yes.
that one, like, why does it bond differently?
What?
Why does it bond? Is it because they're both gases?
Why do things bond differently?
Like, you know how, like, that one has, like, one of them is, like, it didn't bond?
Oh, why does it have an unshared pair? It's because, you know, like when you're doing the Lewis structure of nitrogen, it's 5 frog hops over, so it gets 5 electrons. You get one on each side before they double up. So on one side it's doubled up and it's got 2 electrons, and on 3 sides it only has 1 dot. Wherever there's 1 dot is where it wants to bond. If it has 2 dots, it doesn't bond there because only 2 electrons can go in an orbital, remember? And so that's why it has an unshared pair. So this one, the nitrogen has an unshared pair, it's right there. And it's bent.
So, like, the one that, like, bends like this, is that, like, the unshared?
That one's the unshared pair. The thing that looks like an alien head is the unshared pair. It draws a little cloud with 2 dots in it, or just a cloud like that. Okay. And that is something, well, you know, we really didn't go into much with the honors, so it's another place where it's a little different for AP. Okay, what about if it has 4 electron domains? Then the shape is tetrahedron. You could have 4 bonding domains and no unshared pairs. An example would be that nice little tetrahedron, and that's our methane, classic tetrahedron shaped molecule. We could have 4 domains and 3 of them can bond, and we could have 1 unshared pair, and that would give us trigonal planar like ammonia, NH3. We could also have 4 electron domains. 2 of them can bond and 2 of them could be unshared pairs, and then it's bent. And our example of that is water, H2O. Okay, good so far? Honors plus just a little bit. Effects of non-bonding electrons on multiple bonds or on bond angles. So non-bonding pairs are physically greater, I'm going to use, than bonding pairs. So they're bigger. They're physically bigger, and that causes them to be a little stronger, and they push the other bonds away a little bit more. So like here, we had a tetrahedron with 109.5. Here, this is a little stronger, and it shoves these away a little bit more. And so it changes those bonds to be a little closer. I think it's 107 in ammonia. Okay, so it's a little bit greater, a little bit more powerful. That's why we got our guy drinking protein here. So electrons in non-bonding pairs of multiple bonds repel more than electrons in single bonds. So here is methane. Our regular tetrahedron, 109.5. Here's ammonia, squishes it a little bit more, 107 degrees. Here we are with oxygen. 2 of them squish these even closer together. It's 104.5. And then here is one where it's got a double bond, and then these are single bonds. This double bond can squish it a little bit more that way. So just think about double bonds are a little bit stronger. So these bonds to the double bond are 124.3. This is not a regular trigonal planar where it'd all be 120. It's 124.3, and this is 111. Says 4, but that doesn't add up to be 100. 124.3, 124.3, that's 248.6. So this should be, okay, it says 0.4. 111.4. It's going to be close enough because 6 and 4 is 10. 111.4. Okay? So unshared pairs and double bonds squish everything away from it a little bit more. Molecules with expanded valence shells. So these are our dog toy ones. Oh, it's gonna be. Okay, so what about if they're bigger? Okay, so total electron domains for this one. Oh, I forgot this. Atoms that have expanded octets have 5 electron domains, trigonal bipyramid, or 6 electron domains, octahedral electron domain geometry. So it is the number is more than 3 is our things going around it. More than a little bit more. Okay, so if you have 5 electron domains, you could have 5 bonding domains and 0 non-bonding domains, and we get the trigonal bipyramid. And the example of that is PCl5, phosphorus pentachloride. Okay? So we could also have 5 domains. We could have 4 of them bonding and 1 unshared pair like that. And that's called a seesaw. It's a seesaw shape. Okay, and our example of that is SF4. having a hard time going. Seems like we're going nice and fast here. Are we good still? Do you see how that kind of looks like a seesaw? It could totter.
I don't know.
Were y'all ever allowed to play on seesaws as kids? They're hard to find now. They're considered unsafe. So you have to find an old-fashioned unsafe playground. They were rare. They used to have one in Hiram when my boys were little, but then they got rid of it and made it safe. The
I see them all the time.
the one over there. All right. So next, page 4. Make sure I'm at the right one. Yep. Okay. So total electric domains. Total electron domains. We could also have 5 of them. We could have 3 bonding and 2 unshared pairs, and that's how you get T-shaped. So our example is ClF3. So T-shaped exists. Remember when I held 3, I said, is this as far as it can get? But the reason why is because it's got 2 unshared pairs. So you also could have 5 electron domains. You can have 2 bond and 3 unshared pair like that, and it ends up being linear. And our example of that is this. Okay. How do we feel about that? Good? We can imagine that? Okay. So we could also have 6 domains. 6 could bond, no unshared pair, and you get the octahedron. Octahedron. I have to say it slow, get all the syllables in there. So there's our example molecule. We could have 6, 5 could bond and 1 not bond. And our then is a square pyramid. It's like a square pyramid base with 1 going up top. Our example is BRF5. Or we could have 6. We could have 4 bond and 2 unshared pairs, and that is called a square planar. And our example is XeF4. Okay? Now, what about when it's real big like this? The interior atoms of more complicated molecules can be dealt with by using VSEPR. So what you do is you just imagine each part of it and think about what it's going to do. So I have cut, so imagine you cut that off. Then you've got this carbon with 4 things around it. So what shape do you think this part of the molecule will have with 4? Tetrahedron. So this part down here is a tetrahedron. Okay. So here I've got a carbon with 3 things around it. So what shape is it going to be?
Trigonal planar.
Yes. And here, you chop it off, it is oxygen, and oxygen has 4 things around it. If it were double bonds, it'd be linear, but they're not double bonds, it is 4 things around it. So it's like the 4 things are tetrahedral shape, or you can look at just this part of it as bent. We'll put both. We'll say bent / tetrahedral. It's really more bent because it's going to be those closer bond angles of bent. So it's going to be bent down here. It'll be in a little peace sign in the middle, and it'll look like a little puppy dog methane down there. Now we can imagine what it looks like, can't we? We could kind of imagine its 3D geometry. Okay? Section 9.3, molecular shapes. Polar molecules interact with electric fields. Binary compounds are polar if their centers of negative and positive charge do not coincide. Okay, so let me tell you what that is in more plain English. Symmetrical molecules, usually if they're completely symmetrical, all their charges cancel out and they're not polar. Polar molecules are asymmetrical, where they have a positive end and a negative end. That is what it is saying. So if they have a positive and negative field end, then they would interact with the electrical field. Okay? And binary compounds are polar if their centers of negative and positive charge do not coincide. If it doesn't, cancel each other out is what we're talking about. All right, moving on to page 5. Okay, so this is CO2. I'm going to write it over here because you can actually read it on your paper, but it's really hard to read. Do you think with this carbon in the middle, oxygens on each side, you can see the arrows that indicate polarity are equal and opposite. Do you think this molecule is polar or non-polar?
Non-polar.
Non-polar because
It like has both sides.
it's like they cancel each other out. They're pulling evenly, so it's non-polar. The bonds are polar. The bonds spend more time with the oxygen than they do with the carbon, but they cancel each other out. They're pulling each other exactly evenly. And if you look at it, this is the two of them pulling. Do you see how everything's symmetrical? So if it's symmetrical, no place where the charge is concentrated, non-polar.
So are those supposed to be the same thing?
It is the same thing. Carbon, oxygen, carbon, oxygen.
But like the bottom thing?
Yes, this is it drawn with sticks, and that's with the electron clouds all smooshed together. And in your book, it shows it in color. So, all right, so this one. Do we think that one is polar or non-polar? It's water.
Polar.
It's polar. You probably memorized that water is polar, right? But we can see it. We have the positive here and the negative there, and they're going that way. It gives us an overall polarity of the positive centered here and the negative going that way, so it's polar. We can also see here, it is not nice and symmetrical. It's a little blob. Okay, here's another one. HCl. Do you think it's polar or non-polar?
Polar. Because it's not on
Polar.
both sides, it's just on one side.
Right, it's polar because it's not on both sides, it's just one. And if you look carefully, there's a little arrow with the plus on that side and the minus on that side, and there's nothing to counteract it. So this one is polar. Okay, moving on around. Let's do this one. This is ammonia. Do you think it would be polar or non-polar?
I think it's non-polar. I mean,
Polar.
non-polar.
Polar, why?
There's nothing on the top.
There's nothing on the top. The arrows are all pointing up and toward it. There's nothing to counterbalance it, so it's polar. Okay? How about in the middle here? CCl4. Polar or non-polar?
That's non-polar.
Non-polar, they're all canceling each other out. I'm going to just put NP for non-polar. Okay, how about this one? BF3.
Non-polar.
Non-polar, they're all pulling out exactly equally in the same direction, so it's non-polar. Y'all are doing great with this. How about that one?
That one's polar because the top one pulls more. or
Right, because the top one's bigger and it pulls more. It's not equal. This is, I'll write it right here. It's CH3Cl, and it is polar. Let's make it a big polar. All right, y'all did great with that concept. So the polarity depends on the polarity of the bonds and the geometry of the molecule. Okay, so now we're going to learn a new concept that's new that you didn't learn in honors, covalent bonding and orbital overlap. At least you didn't in my class. I don't know if the scorn taught it or not. Okay, so what a bond actually is, covalent shared bonds, non-electron transfer, formed through sharing electrons by adjacent atoms. So atoms are next to each other and they share. And when they do, the orbitals overlap to form covalent bonds. So here we have a 1s, an atom with an electron in 1s. And then we have another atom that's got 1 electron in 1s. And then they squish together and they overlap and it makes a bond. And this is hydrogen bonded to hydrogen. It's hydrogen gas. So you can see where it's like a Venn diagram, and where they overlap is the bond. Can you see it on the paper, the little bitty Venn diagram? Okay. Our next one, this one we have a 1s bond and a 3p bond overlapping. And this is what you get with hydrogen bonded to chlorine. That's what bonds there. Hydrogen and chlorine, and the chlorine's got these unshared pairs. But that's what it would look like as it bonds. Here we've got 2 3p's overlapping. See their little Venn diagram in the middle? And this would be like chlorine bonded to chlorine. So this is the Cl2 molecule. Okay, how do we feel about that? Can we imagine that? Okay. The change in potential energy as 2 hydrogen atoms combine to form a hydrogen gas molecule. So let me tell you what this is. There is a certain amount of Venn diagram of overlap that makes it happy. That's why we got a happy little frog saying great. If it's not enough, not happy. Too much, not happy. It's this perfect amount of overlap that makes the charges happy. Because remember, these are both negative. And so you can't squish them too close or there'll be repelling. But at the same time, the atom wants to make the bond. It wants to feel like it's got the octet. So there's just this perfect little amount of overlap that's the bond. Okay, so there's a little graph of it. Okay, and let me see if I can draw it good here. It goes like that. Whoop. And then it goes like this. Whoop. And then it goes like that. Whoop. Always more fun with sound effects. You can say whoop as you draw yours. Okay, so there is an optimal distance. And it is that. That's the optimal distance. That's where the energy is the least. That's where the line comes down the lowest. We good with that idea? No, we're doing so good. So yay, it says, bravo, this is how we like the bond to be. The atoms are happy. 9.5. Hybrid orbitals. Now, I introduced this concept. I like to introduce concepts and then kind of circle back to them, reinforce them, spiral a little bit. And I told you before, when we were talking about electron dot diagram for carbon and why there's one on each side, when you would think there wouldn't be, but it's because they like the half full kind of thing. But also, I told you then that orbitals can be mixed. You can mix the orbitals together and get a new shape. And that's hybrid orbitals, okay? To apply the idea of orbital overlap in valence bond theory to polyatomic molecules, we need to introduce the concept of hybrid orbitals. Hybrid orbitals, okay? So sp hybrid orbital. Consider beryllium in its ground electron state. It would not be able to form bonds because it has no singly occupied orbitals. And this goes back to Lily's question when she was talking about why is there like 2 dots and then in other places there's bonds. And it's, remember, if there is if there's an unshared pair, it doesn't bond there. It only wants to bond where there's just 1 electron ready to share into the pair, okay? So if we were to do the ground state of beryllium, if we were just going to do its electron configuration, y'all look at the periodic table and tell me what the electron configuration of beryllium is. One. Oh, I'm going to do it a different way. Do more Phyllis sound effects. 1s2, so I'm going to draw my arrows, and then what is it? 2s2. You can put your little superscript, and it would have 2 arrows, and it would make no bonds. Do you see that? Everything's got 2 arrows. It only bonds where there's 1. Okay, so it could go. So that's what it theoretically does, but it's not what it does. So the other thing it could do is it could do 1s2, 2s1, and 2p1. It could promote 1. But remember, what is nature like? Nature likes balance, and this is not symmetrical. S's and P's are different, and nature wants this little thing, beryllium with 2 fluorides, to be linear and to be balanced, and it would not be balanced. So this is not. So this is not. This is unbalanced. So this one is no, that doesn't happen. No, that doesn't happen either. This is what it does. Is it takes the shape of the S and the shape of the P and it mixes them together and makes a brand new kind of orbital called an SP. And so then it's got 1s2, and then it's got 1s2, sp2, and now it's got 2 nice and symmetrical places ready to bond. So mixing the S and P orbital yields 2 degenerate orbitals. It's called degenerate orbitals, which I think is kind of funny. It made me think of the wrestlers, D-Generation X, Triple H, Shawn Michaels, so I put a little DX there.
Shawn Michaels.
Only people who know wrestling would understand why there's a DX there. If not, just go, it's degenerate. And you can draw yourself something else to remember it's called degenerate. Okay? So, mixing the S and P makes a new kind of orbital. There's an S, there's a P, and when they get mixed, they look like that. And they can go either way. So, S plus P equals SPs. You're mixing it like chocolate milk. So we got our little glass of chocolate milk there. Okay? These 2 degenerate orbitals align themselves 180 degrees from each other and 90 degrees from the 2 remaining unhybridized p orbitals. So there is our molecule, all nice and in a line, symmetrical, nature-liking balance. Now this is considered a hard chemistry idea, but I don't think it's that hard. Oh, I forgot to tell y'all another thing to use to imagine it. Go all the way back. Did I draw it back here? Yes. Okay, so this little balloon, what this has to do. Some teachers, when they teach this, instead of giving out marshmallows and pretzels, will give everybody little water balloons and have them blow them up and then hold them. And the water balloons will push away from each other. They just have air in them, not water. And they'll push away from each other as far as possible. If you take 2, they'll naturally make a line. If you take 3, they'll naturally make a little trigonal pyramid shape. If you take 4, it'll just pop itself into a nice little tetrahedron. So one way to think of this that will help you is imagining these as balloons. Okay? Forgot to tell y'all that. Back to where we were. All right, so here are our balloons aligning themselves away from each other. Now you can also have 3 orbitals blend together. They are called 3 sp2 hybrid orbitals are formed from hybridization of 1s and 2p orbitals. So we can, if you had a ground state of sp2, they would first be like that, but then they could promote it where it's like that, and then they mix together. So you have 3 exactly the same orbitals ready to be bound. You can also have that with sp3. So you start off with the ground state, what you think would happen, but then you can promote one and then mix them, and they're all the same. And this is, you should be very in awe